Okay. Okay, so press OK here, otherwise this will not work. All right, so welcome everyone. We're very pleased today to have Dvira Segal from the University of Toronto with us. She's actually a theoretical chemical physicist, if that's the correct term. But she's an expert in many, many things that are very related to what we're interested in. Among these are quantum transport and dissipation. Energy transfer at the nanoscale, quantum statistical mechanics, especially quantum thermodynamics, and many, many other things. So she got her PhD from Tel Aviv University, then did a postdoc at Columbia. No, before that she did a postdoc at the Weizmann Institute, and then a postdoc at the Columbia, and now she's at Toronto. And without further ado, please go ahead.
Oh, thank you very much. Oops, my surprise. Okay, thank you very much for inviting me. Indeed, it's an interesting forum. I'm not doing particle physics. I hope you will find it interesting or relevant to what you do, and I'm very happy for this interactive forum. Please feel free to ask questions. So the specific title, Bath Engineering Magnetic Order in Quantum Spin Chains, an analytic approach. That's really the main story. A tool that was developed in my group where we wanted to be able to say something analytically, or at least provide some understanding beyond simulations about the impact of, as we have said, as was mentioned before, dissipation or generally environmental effects on magnetic order. The true title, or the higher level title, is just Quantum Dissipative Dynamics Beyond Weak System Bath Coupling. That's a real challenge that we tried to address in this project. So we are thinking about whether it's a quantum spin chain or general impurity model. I will show some examples coupled to an environment, and we are interested to go beyond what is called weak system bath coupling limit, a limit where I will describe it more, but that's where the challenge lies. So as was mentioned, I am sitting mainly in the Department of Chemistry and also Physics. And as such, I want to maybe make a little bit of connection. How does this blue title on magnetic order in quantum spin chain connects to chemistry, or at least how my trajectory, how my research evolved into this topic? So indeed, I'm coming from a chemistry background. After a short while, I realized experimental synthetic chemistry was not for me, or they realized it was not for me, so I moved to more theoretical aspects. In chemistry, of course, the main focus is on reactions. So, and reactions means that we have electrons moving around, charge transfer, and we have energy dissipated, energy considerations that have to be taken into account. And as for the product, we need to consider energy dissipation. So I just copied here a simple reaction from Britannica to put some example. So as I said, instead of doing it in the lab, I moved to simple models, and the models became more and more simple, canonical, let's call them. And one of the basic model that, okay, it takes a little bit while to explain, so I will not do it, but one of the very basic model that actually connects to charge transfer reactions in condensed phases is having a two-level system. You can call it a qubit or a spin. So these are these two levels, and the delta is supposed to represent the splitting. So that's our system, again, connected to the reaction. And the process, or whatever is a quantum process here, the charge transfer, happens in an environment. So that's this bluish cloud here. I hope you can see my mouse. Representing an environment at a certain temperature. And of course, there are other features of the environments that one needs to capture, density of states, and so on. This circle in between, maybe a little bit confusing, is just to represent the interaction between the system and the environment, which we can tune if it's in theory, playing with different coupling operators. So that was a starting point, starting from chemistry-motivated questions of reaction dynamics, moving on to more basic models that I got more and more, became more and more interesting for me and enjoyable. And indeed, these questions of going beyond weak system-bath coupling are very relevant in this scenario and in chemistry situations. If you have a reaction taking place in solution, yeah, you cannot assume that the solution is not important. This environment is dissipative and very important for the reaction. So moving from there, actually we developed a method that was for what I may call impurity model. Yeah, this spin qubit two-level system. But then we quickly realized that we can generalize, we can apply the method to many other interesting problems. That's where it became very enchanting. For example, this canonical quantum spin models. So in this picture, yes, yeah, we have this, let's say, one-dimensional, but it can be more, can be two-dimensional. But let's imagine we have just a one-dimensional chain of spins, as in the regular Heisenberg model, for example, with that type of coupling and maybe magnetic field and so on. But it's not isolated from an environment. It's coupled to other modes, whether a cavity mode or lattice phonons and so on. And the question is, how does the environment impact the magnetic order? So let me start by acknowledging the people who contributed, and I think it also would help maybe understand the trajectory of this project. I think at least I find it helpful when I read sometimes papers. They sound wonderful, and I wonder how did people get to that result, to this project. So the concrete project that I will describe, yeah, that's the title, Bath Engineering Magnetic Order. It's on the archive, and it was accepted today to Fizrevlet. Brett, a graduate student in my group, was the one leading it. It was done together with Nick, who previously came up with the principles of the method, and Marlon was also, he's a graduate, postdoctoral fellow in the group and involved in simulations. So indeed, this was 24. Before that, a year ago, we worked with Hassan Nazir from the University of Manchester. And that project really is where the formulations, the methodology, was developed and formulated with examples. So the method that I will describe is called effective Hamiltonian theory. It was developed there for impurity models. That's why I put again this spin coupled to an environment. That this was the type of applications we were thinking over there, applications related to quantum thermodynamics also. But then that's where Brett came to my group and he said, he is interested in condensed matter, quantum materials applications, and he realized we could just use the same method, generalize it, extend it, and understand these types of systems. But going even to 22, as you can see, the project starts more maybe modestly with Fizrevi, if that tells us, I don't know if that's a measure for anything. So I've had an undergraduate student in my group, Felix, and he worked with Nick. Yeah, and then it was a concrete question that we asked about a certain quantum machine, quantum refrigerator, and we wanted to understand the impact of strong system-bath coupling effects on the functionality, on the cooling window, on the cooling performance. So it really developed by asking very concrete question, and then seeing the structure of the method coming to place, developing it further, and then realizing there are more applications, a class of applications suddenly opened up, and now we have many more ideas. So yeah, I hope this shows something about the development of the project. So more broadly about quantum dissipative systems, at least from my background, where from chemistry, quantum thermodynamics, where people look at it. So I mentioned already, we started by thinking about quantum absorption refrigerator. It's a very basic model that is depicted here, three-level system. I don't have time, at least within the 30 minutes, but I can stay longer, of course, to describe it. But that is an open quantum system. And the question was about performance beyond the weak coupling limit. Other examples for open quantum systems could be coupling to fermionic leads. So these circles are supposed to represent quantum dots. So thinking about thermoelectric junctions where we have charge transport due to chemical potential difference and temperature difference. One can think about the system as a thermoelectric power generator, and the different environments could be the fermionic leads, the metals, as well as the substrate phonons. So the method, again, is Fizrev X quantum or exemplified this effective Hamiltonian technique on such examples. But just to mention other areas where people think about strong or going beyond weak system math coupling, many people came to the field motivated by biological questions, biological applications, specifically in the last 15 years about photosynthetic systems. So that's a very rough image just to show, if a photon is absorbed, and that's now the pigment becomes red, excited, and then the exit, there is an exciton generated, an electron hole pair, and now it can hop around. So that's where you see this red circle moving around, and eventually the excitation is captured where it should be for the reaction. But the main issue here is that while you would like maybe to model it with a few level systems, something clean, this exciton transport between pigments happen in a very complex protein environment, which again is active, it participates in the process, and that's where people realized you cannot model it with, if you are familiar with Lindblad equations or other Redfield, simpler weak coupling techniques. So that led also to many people consider developing techniques for strong coupling and trying to understand signatures of strong coupling. So I showed, hopefully convinced you there are different types of examples where strong coupling could be interesting for the performance of quantum machines, biological system. We'll talk about the example here, the spin chains. How do we generally deal, again, for my field, I know there are many, many techniques with open quantum systems. So there are many different techniques, classes of techniques, starting from numerically exact tools. People have developed different flavors of Monte Carlo approaches, path integrals, wave function methods, master equation techniques of different levels of hierarchy. And then there are many perturbative tools in different parameters. In chemistry, the field of mixed or hybrid quantum classical methods is also quite interesting. The method that I will describe today falls into this, in between the perturbative tools. So it sounds maybe very tedious. It's not. What we are going to do, I will not dwell here actually on the perturbative aspect, but the key here is that in order to make this perturbative approach successful, the best is to think first about the Hamiltonian and transform it to a favorable basis or favorable representation, such as the parameter that you want to perturb, it's not necessary. If you want to go to strong system math coupling, of course, don't do the perturbation series in that parameter. Transform the Hamiltonian such that another parameter which is less interesting to you, which you can assume is weak or small relative to other parameters, can be treated in a perturbative manner. So that's the spirit of the approach. It's let's transform the Hamiltonian, let's manipulate it. It's not just transformation that we did, such that we create a new operator that it's sort of an ansatz that we refer to it as a new system Hamiltonian or an effective system Hamiltonian, and we can treat it now with cheap tools. So again, to mention the field of at least quantum thermodynamics where strong coupling effects were discussed quite heavily. I wanted to show, for example, a book that people, several authors editors participated with many, many different contributions. So as you can see, a big chunk of it, part 4, was dedicated to strongly coupled systems. So now the method that we developed can be applied to study equilibrium problems, steady state, non-equilibrium steady state problems, dynamics. I'm going to focus on equilibrium. So let me define the challenge. If I begin here from this illustration, I have a two-level system, as I mentioned before. I hope it's clear. This delta, again, is just a splitting. It's embedded, immersed in a bath, characterized by temperature T and its modes. It can be, let's say, a bosonic bath. That's an example that we will use later on. Just collection of independent harmonic oscillators. And we assume that overall, the total system is going to be at a canonical state. What we are interested at is only the state of the system, S. So S is my spin, two-level system. I would like to study its properties. And since the total system, as I've said, I know the state, what I need to do, I just need to trace, need to trace over the bath, and then I get the state of my system. So that's what I want to calculate. And as I've said, people calculate this object with Monte Carlo approaches, for example. What do I know about the state of my system? If the interaction energy is very weak, the weakest I can take it, then the state of the system is really just the Gibbs state with respect to the system Hamiltonian. Yeah, I can neglect the interaction energy in the total Hamiltonian. This total Hamiltonian, again, I hope you can see my mouse. Total Hamiltonian includes the Hamiltonian of the system, the bath, and their interaction. And if I'm in this ultra weak coupling limit, I really just do the brutal thing, ignoring the interaction energy. And I end up with this expression as an approximation to the state of my system. Lambda here will be the parameter that I use to represent the interaction energy. Okay, so I cannot see your face if you are with me or not, but feel free to ask questions or clarifications. So that's ultra weak coupling limit. Well, again, we get the Gibbs state. There are other methods were developed, as I've said, perturbative, or actually people also capture the ultra strong coupling limit. But generally, the question of what do we have beyond the weak coupling limit? What do we have beyond this state that we know is really just the limit is an open question. And that's what we wanted to address in this project. So what I will show you, I mean, that's the approach that we took. We came up with a transformation approach, starting with this bare system Hamiltonian and coming up with an operator that we refer to as HS effective. So we refer to it as an effective system Hamiltonian. And what we argue is that it serves to build the equilibrium state of the system. So we showed how to transform this Hamiltonian into an effective one. And now you can make this weak coupling approximation and still get results beyond the weak coupling. And the main secret is that what we do is we manage to move, how should I say, move or push, pull this lambda parameter, the interaction energy, from this connection, from this boundary inside the HS effective. And so it's going to change, it's going to renormalize levels, change parameters, but now the impact of this interaction energy is inside the effective Hamiltonian instead of in the connection. Okay, I have to start moving on. I will tell you about the principles of the effective Hamiltonian method, and I think I will focus only on the blue, which is what I promised in the title, but just to show it here, and if there are questions later, I can touch it. There are some nice results for this system. What's the equilibrium state? How does it change from the Gibbs state? But I will focus on the bath engineering magnetic order. We also have results for dynamics. Oops. So I will begin with the principles of the method. I will try not to be too technical. Okay. The starting point is a system, HS, Hamiltonian, interacting with a bath. And I made this line very thick to indicate that the interaction energy can be strong. So that's the starting point A. What we did here were 3 steps. In step B, I forgot to mention, the Hamiltonian that we work here, though it can be generalized, is a collection of harmonic oscillators. So in step B, what we do, we identify an important collective, what we call reaction coordinate from the bath, and we simply absorb it into the system. So it's a collective coordinate from the bath, which now is bath prime, because it's missing 1 degree of freedom. And now it's pulled out, and we extended the Hilbert space of the system. In stage 3, what we did was a rotation of frame. We'll get to that, such as we push this interaction parameters furthermore into HS tilde. And finally, we came up with a truncation. It's really just based on including only the lowest energy levels of the effective Hamiltonian based on temperature considerations. And with that, as you can see now, the line is dotted. That was our objective, to reach a model where we have an effective Hamiltonian, but weakly coupled to a bath, which we can treat simply in the ultra-weak coupling limit. So I will go over the stages. Okay, hopefully it will be clear. A is just the setup of the problem. So what do we have? Hamiltonian of the system, the bath, and the interaction. Generic system, the bath is made of collection of harmonic oscillators. And the interaction operator that we use, it's given in the form of a system operator, which could be, for example, the polarization or other, if it's a spin, other poly elements of the system Hamiltonian. And these are the displacements of the harmonic oscillator. So that's a very common model in the field. It's important to characterize the bath, and it's done by characterizing it with a density of states, or what we call spectral density function, which is a weighted density of states. These are the interaction parameters for each mode in the bath to the system. So again, it's like a weighted density of states, and we specifically in this project use the Brownian spectral density, but it can be generalized. So this function here, it's depicted in dark color. That's a spectral function of the bath. The center, it's at frequency big omega. So this bath has modes focused, centered around big omega with a width of the function gamma. And as I've said before, the coupling energy to the system is given by this parameter lambda. So that's also given here. So that's just the model. Okay, so now to the actual steps. What we did, the first stage was discussed a lot in starting with chemistry. That's why the name is reaction coordinate. The idea is that you identify an important degree of freedom and you just add it to the system. You just need to redefine where the boundary with the bath is. Instead of here, it should be here. So we do this transformation. You can identify such important degree of freedom. Again, bosonic one, of course, A equation, A dagger and A equation annihilation operators. And now what one can show is that this coupling energy is pushed to this boundary between the system and the reaction coordinate, which is of frequency big omega. So there are two important parameters in this story. One of them is the interaction energy, lambda, as I've mentioned. And it's actually given in terms of the original spectral density function. Once I do this reaction coordinate transformation, instead of the original spectral density function, I have now a new bath, B prime, with a different spectral density function. And the properties of the function dictate these two parameters, lambda and where is it, omega. And as I've said, the residual bath has a different spectral function. In our case, for example, it becomes ohmic. So we started with Brownian bath, and we ended up with a different one. It's not to scale in the sense that we are going to use a narrow Brownian function. So it's going to be weak coupling now with respect to the residual bath. The next stage, which, okay, it's a technical, I will not get to more intuition. We did another transformation, just a polar on shift transformation on this reaction coordinate. What it does is to disconnect or to weaken this contact. And again, it allows us to push this interaction energy into this operator, edges tilde, this effective system Hamiltonian. And now it's built inside instead of being at the contact. So as before, we still think of that as an extended system. So obviously it has a higher Hilbert space of higher dimension than what we started with, coupled to this residual bath. What we see after this stage, it's not yet the final one, is that the model, it's all exact so far. The model includes this new revised system Hamiltonian, this reaction coordinate mode. What we already see, which is very interesting, is that we get a new term. So these steps that we did analytically, just massaging things around, in the new picture, we find that S, which is the operator of the system that couples to the bath, now contributes a term into the system Hamiltonian. We will see later on what it does. And then we have the residual coupling to the bath all here. The final stage is really based on, it's approximate, it's a truncation. We wanted to go back to a simpler system. One can do from here actually numerical simulations. It's not such a terrible problem. Yeah, it's a system with an additional reaction coordinate, additional harmonic mode. But for the analytical flavor of it, what we did was to truncate the energy spectrum of the system. And here I'm just trying to motivate and explain what's the rationale behind. So it's not a precise figure, but the idea is that the system model, we assume that the spin splitting is small relative to the spectral properties of the bath, omega. And as such, we can truncate the spectrum, just keeping the harmonic oscillator in its ground state. It's not exactly that because we shifted already the model, but roughly, if you go to the limit of small lambda, small interaction energy, that's a picture that you just keep energy levels with the harmonic oscillator staying in its ground state. Altogether, with all those steps, I'm not sure I did a great job, but 2 exact transformations and 1 truncation based on taking away high energy levels, just keeping the bottom of the spectrum, the least, the minimal model that is still meaningful here. What we get is that total Hamiltonian includes, as usual, 3 terms, the system, the interaction, and the bath. The system, the Q naught is supposed to represent that I perform this projection onto the ground state of this harmonic mode that I extracted. So that's a new system Hamiltonian, a new operator that I will refer to as effective Hamiltonian, together with a strange term that actually will be very important later. You will see it will generate long-range interactions. And there is an effective interaction to the bath and the bath itself, the residual one. The main, okay, sorry, just trying to move here. Now, the main aspect here of this whole transformation was that we argued, again, we can discuss it later on with more details, that this interaction is weaker compared to where we started with. So now we have a new system, or a modified model for the system, which is weakly coupled to the environment. And since it's now weakly coupled as an approximation, as an ansatz, we are using this ultra-weak coupling limit and assuming that the equilibrium state of the system is given by this effective Hamiltonian. So yes, that's our ansatz, that after this transformation, this effective Hamiltonian provides a good approximation for the state of the system. And we checked it, of course, with simulations. So we apply this process to several impurity models in this Fizev X quantum. We ask questions about equilibrium state, about heat transport, cooling, again, heat transport, as I mentioned, the thermoelectric power generator. But I will focus on the spin chains, and as such, I will actually skip this part because I don't have time. Let's skip it. And I will get now to the blue part, which is a bath engineering magnetic order. Can you tell me, please, how much more time do I have?
So we are at 30 minutes now, but I would suggest we just go on a little more.
Okay.
At least we go through it. Don't worry, we are.
To the main story, sure. Thank you. Okay, to the main story, I will finish it in, I think, 10 minutes. So very simple, the components are, I mentioned, spins, bosonic bath, and we need to decide how we interact with the environment. It's a choice here, sigma x, but we can generalize it, or it is very easy to apply it in other cases. So what I'm going to show you with this technique, it has nice applications. Maybe the theory was a little bit abstract. We are going to start with, let's say, Heisenberg model, which is coupled to an environment in a global way, meaning that all the spins are coupled to one environment, one collective bath. And we are going to start with an antiferromagnetic order, and we will show that because as we couple to the bath more and more strongly, the order changes to become ferromagnetic. And we can see it without doing simulations. We can see it already at the level of the effective Hamiltonian. We can continue playing with other cases. The method is very flexible, very easy to apply. For example, we can think about a system where I'm coupled to the bath, but not collectively. It's more of a local coupling. Maybe not every spin by itself has its own local. Maybe there are still some correlations. The bath does impact two spins at a time, and then these are independent environments. And again, we can show change of magnetic order now from an antiferromagnet to an extended Neel. And the method, as I've said, very flexible. We can also look at beyond one dimension. So the fully connected Ising model, it can be Heisenberg model, but we just for simplicity did it for the Ising model, and we'll show quantum phase transition. So now indeed, the actual practice, what do we do? Let's say we start with Heisenberg model. So we have the magnetic field, we have this J, or this coupling between the different spins, where alpha is X, Y, Z, the spin components, and I is an index of the spin along the chain. And it's really important to identify how do you couple to the environment. So as I've said in the first model, it's a global coupling. So all my spins couple to one single bath. We exercise these steps. It's all in this archive paper. And post-mapping, this is a beautiful part. We just get a closed form expression for the system Hamiltonian that we can analyze. And let's see what we get. We see that this magnetic splitting is now renormalized. I gave it a name tilde. And what happens is that it's being suppressed. So it's an effective suppression of the magnetic splitting due to the environment. Lambda, again, is a parameter of the interaction. Another impact of the environment is to change these J's. What happens to them is they are starting to mix. Yeah, the X, the Y, and Z are mixing and also changing in magnitude. But the most interesting part is the last one, which tells me that, sorry, I have to move things around here. Yeah, that I get, I get this long-range interaction. So if you take a look at this operator here, when I square it, it means that all my spins in the chain are going to interact and it's negative. And that means that I'm going to get a ferromagnetic interaction between all my spins. So that's actually, I would say, one of the, sort of the takeaway of this, what this method can do. Analytically, we start with a certain Hamiltonian coupled to the environment. We ask, what's the impact? We get a new Hamiltonian. And already we can see that we are going to generate a ferromagnetic interaction between all the spins. And as such, we expect that when we increase the interaction, the order will change. So indeed, I'm showing here the structure factor in the X direction, because that's the direction of the bath as a function of the interaction energy, starting from an antiferromagnetic order and going to one means that here it's a ferromagnet. And you can see it also by looking at just these correlations between all the spins on the chain, I and J. So again, it starts with the spins all being in an antiferromagnetic order and at strong coupling here. They are all aligned in the same direction. Okay, I will skip the right panel, not so important. Another example that is maybe fun, as I've mentioned, you can play with the environment. It can interact individually with each spin, or maybe you have these grains that interact with the same environment. So that's the case that we considered here. Independent environments for each pair. Same Hamiltonian as before, or actually, let's simplify it. So now it's going to be an Ising model. I didn't write it back again. But what we find post-mapping is, again, all the magnetic field terms are going to be suppressed. But more importantly, or more interestingly, what we see is these terms here become ferromagnetic interactions, while these terms between the pairs are still antiferromagnetic. And as such, what we see is we start with an antiferromagnetic order for the full chain, and eventually you get to this extended Neel stage, which means that these two spins are aligned, and then the next two are aligned in the opposite way, because between them there is an antiferromagnetic interaction. And again, each pair between them, they are ordered, but you flip the order because of the original interaction not being changed here. So the beauty of the method, one can do other examples. We did also the fully connected model. The beauty is that it's fully analytical. We can see, we can already see what phases, or we can, if you want to engineer a certain phase, I don't know how practical it is. I hope in the crowds there are not experimentalists who are going to be too critical, but in principle, we can mathematically find out what operator you have to couple to the bath with, what should be the quality of the bath, how to couple to it, and increasing coupling strength could tell you how to, which phase you're going to see. So this is the last example of the fully connected Ising model. So I started with this model here where all spins are coupled, all of them, but just an Ising example to simplify it. And the effective, analytically, we find the effective Hamiltonian to be such that, again, you get this due to the environment. Lambda, again, is a system bath coupling parameter. You see that eventually at very strong coupling, this will dominate, which means that we will get the ferromagnetic order here at strong coupling. But at weak coupling, we start from the antiferromagnet. And this is a quantum phase transition. It's independent of the number of spins. It's independent of temperature. That's why we have all those lines, just checking the behavior. So it's actually very, very nice that one can see it already. And of course, from here, just from looking at this term, you can identify the point, the critical point, just by checking when it's 0. So just to mention before I go to the summary slide, when we looked at the literature, it was quite amazing. We saw many different studies. Each of them, I mentioned here 3 models, but there were many, many models of these dissipative spin chains, and different studies, each devoted to one spin chain coupled to a bath with a certain specific connectivity, and the bath had to be with specific spectral function, let's say super-ohmic or sub-ohmic. So each study, they did it with, let's say, Monte Carlo. It had to be, one needed to come up front and decide all those properties, all those details, and do the simulation. While this method is, of course, not exact. In the manuscript, you can see we did benchmarking, and there are some limitations, of course, but it gives you a nice flavor of what to expect. So with that, okay, a little bit over time, or 10 minutes over time, and let me conclude. This technique is quite versatile. It's analytic. It's non-perturbative. In fact, the ultra-strong coupling limit we showed in the impurity model is exact, which is still strange to us. One can apply it to large spins. One can apply it to high dimensions, which are things that we are now doing, as well as looking at dissipative fermionic chains. One challenge is to focus on dynamics, but I will not get to that. And finally, again, I would like to thank the students in the group and collaborators. And of course, thank you for your patience. Thanks. That's it.
Thank you very much for this very insightful talk. We have time for questions. Jojo.
Yeah, thank you. Can you go back to your slides where you show us the first step? I mean, the technical discussion.
Mm-hmm. Yeah. Oops, that's the benchmarking. Sorry, okay, almost A. So A was the setup of the problem. Yeah.
Yes.
Oh.
Yeah.
Mm-hmm.
So, so is what you call the operator A on your next slides is the sum over K times, sum over K, the CK?
Oh, yeah, one is defining, this reaction coordinate,
I see. But so I mean the reason why you could do this reaction coordinate and pull out the most important environment degrees of freedom is because you're assuming the interaction between the system and environment goes like S times a bunch of operators, right? So if the S now also depends on K and put it inside the sum over K, can you still do this trick?
Okay. Generalizing this approach to other. Let me even tell you another case which we are now working, which we cannot take. It's not super trivial. We realized that we even have a problem if you, let's say, couple to 2 environments with non-commuting operators. That's also right now, it's not a trivial extension. So to your specific questions, if the system couples differently to different modes, that would require thinking how to define, okay, here we indeed extract one mode. Let me just mention that in principle, one can extract more than one if, if you realize that you need, there are several components of the spectrum that are important, or people also exercise it fully numerically by doing this iteratively, chain mapping. So as it is here, no, we cannot do what you suggested.
Okay.
Yeah.
Thank you.
More questions? Actually, I have a question. So the effective Hamiltonian that you're describing, I think Harry Miller calls this the Hamiltonian of mean force. But in our community, it's called the entanglement Hamiltonian. And in at least in the zero temperature limit, there's a prediction for it from quantum field theory, which is the Bisognano-Wichmann theorem. And I was wondering if, so that's an analytic prediction. I was wondering if you're aware of that and if you think it's consistent with your.
I am not familiar with what you mentioned from your field. I'm familiar exactly with Harry Miller's Harry's work. Yeah, exactly. That's the Hamiltonian of mean force. I didn't use this language. I wasn't sure if people are familiar. Yeah, but the idea is that this operator, which we use to calculate the state of the system, it's also called the Hamiltonian of mean force. I'm not familiar with the technique that you mentioned. So it's for zero temperature, which is relevant.
It's true for any quantum state, but there's a paper from 2000, but maybe that's too technical, and I'll just write you an email.
Okay. Yeah, I'm curious.
But yeah, if there are more questions.
Yeah, I have a quick one about this slide. So I mean, in the end, the system density matrix is as written. But do you assume the capital omega is large, so the new interaction is weak, or you can prove the capital omega is large?
Yeah, we come up with should I call it class of models or setup that here we can describe. It is indeed of a bath where omega is a largest energy scale. So that's the type of the types of bath that we consider. So it has to be large relative to other parameters. However, when we did simulations, for example, for the spin impurity, we took in simulations lambda to be large, like to go to the large, strong, ultra strong, what is called ultra strong coupling limit. And we actually got the exact results, exact in the sense that we saw that other people derived the result, and it's the work of Janet Anders, if people are familiar. And this technique did reproduce the result of the ultra strong coupling limit, to our surprise. So it's still something that we are trying to understand, even though the approximation that we make is such that this has to be the largest energy scale. We can actually go to large lambda, very large. And compared to other techniques, we realize that in simulations or even analytically, it works very well.
Any more questions? No, I think that we'll stop the recording and we'll thank our speaker again.